in the IFAE, the institute in front of us, as first as a Marie Curie fellow and then as one Galaxy fellow. So today she will talk us about galaxy classification and new evolutionary patterns. So,
thank you, Stefano, for this nice introduction. So some of you have already known me through the collaboration of TAWU survey, but my role here now is not focused on the PAUS survey, but to work on the AGNs with Mar. So literally Mar dragged me to the science of black holes, and I love this topic and love her for doing this. But today I would like to rather present my journey, why I'm here and what drives me to end up with black holes, rather on what we are doing with Mar. I suppose that there will be still another time to present nice work which we have done together. But let me start what brings me here. And everything starts with the classifications. So the classification is one of the principles that drives the science, and not only in the astrophysics, but to analyze different things, we have to find a common feature to gather objects which shows the same properties. So almost 100 years ago, Hubble has proposed the first scheme of the galaxy classification, which still holds, although all the advantage that we have done, the nomenclature introduced by Hubble is still commonly used, although we know that the classification is oversimplified. So we know that today observed structures of galaxies are far complex than dividing them into 2 or 3 galaxy groups. However, we still lack of knowledge and tools how to do that properly, how to extract the important information and to classify galaxies in the meaningful galaxy types showing different properties. And moreover, the other outstanding question is, what is the past history of the galaxies? So we know quite well galaxies that are nearby, but what if we move into the past history of the universe? If these different types of galaxies still holds when we move in the half at the half of the age of the universe or to the first galaxies, does it really show so many different structures? So, of course, looking back into the history is really difficult because we are still not having good images of the galaxies. So these all beautiful galaxies that we observed at local universe at higher redshift, they are simple dots on the images. So astronomers handle this and use other properties to classify galaxies at higher redshift beyond the local universe. And one of the standard methods used for this purpose is the color magnitude plot. And we are used to distinguish red galaxies, which are mostly passive and elliptical galaxies, blue galaxies, which correspond to star-forming spiral galaxies, and sometimes we dare to also distinguish a class of transition galaxies of the green galaxies. And honestly, this plot was the first thing that motivated me to think why we are using only two-dimensional space and shortcuts to differentiate different types of galaxies. During my PhD, I was analyzing red passive galaxies, And most of my work, I was struggling with the proper selection of the sample, how complete it is, how contaminated it is. And it occurred that using different colors, this leads to different samples of red galaxies. Moreover, different samples of red galaxies selected different methods lead to different results. So how we can conclude the science if it's so sensitive to the selection of the sources that we are dealing with that? So I was thinking, okay, but we have the tools. We can benefit from all the information that we have about the galaxies. We don't have to use different selections methods and try to compare them. Why we don't try to combine them into one selection method? And if we see the bimodalities in galaxy distribution in different colors, we don't have to use only two of them, right? So as I was thinking, I decided to try. So how to do that? Thanks to machine learning algorithms, it's quite easy. So machine learning tools are quite novel, but generally we can distinguish two different machine learning tools, supervised and unsupervised. Basically, supervised methods need the training sample. So the objects which we already know which type are. Other method is unsupervised. So basically, we don't have to know the type. We don't need any prior assumptions about that. The disadvantage of the supervised method is that first, we need a priori the training sample. We need the classification of some sources at least. Second, the outcome will be as good as the training sample. If the training sample was already contaminated, not complete, we will just have the same outcome and pass this through. And here are coming unsupervised methods, which don't bother about the labels. We are just taking all the information about the galaxy, the source that we have, and trying to find to reduce the dimension and find the space where the clusters are gathering with each other. So I used one of the unsupervised algorithm, which takes all the parameters of constructed from the space constructed from the parameters given for the galaxies, find the latent subspace in which the galaxies are dividing the best, and automatically clustering all the galaxies that we have. So as we have the tools, now we have to have data to use for that. So most of the classification is based on the local universe, because we have more information and we can do the morphologic classification for them. But I would be interested if the Hubble sequence is still preserved at the half of the age of the universe. So I took the advantage of Viper's survey, which is the equivalent at redshift 1 of the large surveys of the local universe, thanks to its large volume and high samplings. So Vipers is a spectroscopic sample which observed almost 100,000 of galaxies up to redshift 1. So we are, thanks to this survey, we are able to trace the evolution from the structures observed at the half of the age of the universe to the well-known sequence in the local universe. Also the advantage of Vipers is that we have a lot of information, additional information about these sources, in particular the multi-wavelength information. So we are having the photometry covering from the near UV to near infrared, and we use this information to do the unsupervised classification. So basically, what I did, I took all the absolute magnitudes from the far UV to the near infrared, normalized to I magnitude, and ask algorithm what is the division between the galaxies. So the algorithm has found 12 classes which follow this the structure of the most passive, most red, ending up on the most blue star forming, and even the AGN. So one can say, okay, we are using magnitudes as an input feature. So of course the algorithm will find some division, but how this is connected with the other physical properties of galaxies. So we also analyze that this separation in the color space is also well reflected in the spectra, where we can see that the reddest galaxies show strong absorption lines, moving to strong emission lines for the blue star forming galaxies. And the same is reflected in the physical processes. So I will go back to describe more particular classes, but first thing that I was was asking myself, okay, we have the spectra of this. We use the spectroscopic redshift as a feature to determine this classification, but we didn't use actually any spectral features to obtain this classification. We use only spectral information to validate the shape of the classification. So the question would be, could we use the same approach to the photometric surveys, as we are living in the era of forthcoming large photometric surveys? It's a great opportunity to have a tool that allows us to distinguish different galaxy types automatically. So we took the photometric redshift of galaxies, of Viper's galaxies, and redo all the classifications. And here is the results. So we can see with the squares, we have the classification that it's based on the spectroscopic redshift, and the points and the error bars corresponds to the clusters, the galaxy classes obtained with the photometric redshift. And we can see that with only with the photometric information, we are really well recreating the shape of this classification. Of course, we are missing some information. For example, with the photometric information, we are not able to find the dusty star-forming galaxy, but we are able to distinguish also the broadline AGN, or even to find out the stars. So I think that this shows a great potential of unsupervised machine learning tools for the future photometric surveys. But then we were thinking, okay, so we managed, we did. We know what galaxy types are at the half of the age of the universe. But how it relates to the well-known Hubble sequence, right? Do we see an evolution? So this is hard task because we don't have the surveys which covers a large redshift ranges. So basically, we have to combine information from different surveys to gain this knowledge. And we had to do that with my PhD student, using the SDSA data and Viper's classification, trying to discover how the galaxy classes changes with redshift. And it seems that Hubble sequence more or less is mirrored at redshift around 1. We found that the classes are broadly consistent, and the differences are just reflecting the gradual internally driving growth of bulges and slow quenching. But as you can see, we can also see that at low redshift, which is here, especially at this transition region between the blue galaxies and red galaxies, there is much more going on than at higher redshift. So we were wondering, okay, so now we know that we can connect low redshift information with intermediate redshift information, but how to gain knowledge when the transition from blue galaxies to red galaxies come and what processes are regulating this? We know that it's very complex processes, but we know that we think that there are different paths for this quenching, but we are not sure how it is driven and at what redshift it occurred. So, with another PhD student, we tried to attempt this task and try to find this points, this phase when the galaxies are transiting and at what redshift it is happening. So as we already gained a little bit of knowledge about how to run properly the unsupervised classification, we also attempt to improve our methodology in the feature space. So this time we didn't use only the photometric information. We wanted to have more complex pictures. So we used all the spectral information. So we feed the algorithm with the spectra of Viper's galaxies and try to find out how galaxy class evolved from redshift 1.2 to redshift 0.4. So this is sort of a schematic picture, but this is still a work in progress. But we have distinguished already 3 main classes: AGN, passive galaxies, and star-forming galaxies. And let's look at the passive galaxies, for example. At redshift 1.2, passive galaxies were quite homogeneous group. Then at redshift 0.8, it has started to divide for 2 classes, which one is more in transition, going into the transition into the green valley, while these are the most passive galaxies. And the same structures can be found for the star-forming galaxies, but not for AGN, what is interesting. So I think that it's also showing really great potential of unsupervised methods in discovering the transition of galaxies and the process that regulates it. Okay, so we know that the process that regulate the transition of galaxies are really complex one. And basically we can divide them for the internal driven or the external one. So my question would be how the environment in which galaxies reside will influence their evolution, and can we Okay, do you hear and see?
Yeah, now we
Okay.
can hear and see you. Thank you.
Okay, but again, this picture is built for the nearby galaxies, for the local universe. And the first question would be, does it hold at higher redshift when the universe was half its age? So thanks to Vipers, again, we can check this. So we derived local density contrast to describe the environment. And already we can see that that we can distinguish different structures in galaxy surveys. We can see the places when the galaxies are grouping into groups and clusters, and the desert, the voids where galaxies are not so frequent. So do we see this relation at higher redshift? We took advantage of our classification and checked that, yes, this is still at place at redshift around 1. So for this verification, we just go with a brief similar standard classification as for local universe was done. So we took only the blue galaxies, the red galaxies, and the green galaxies, and found that when we are moving to high density, the fraction of blue galaxies is dropping, which is compensated by the increase of the fraction of red galaxies and small increase of green galaxies. But we have more complex information. So let's look, for example, for these red galaxies. Our algorithm has found 3 different subclasses of red galaxies. So do we see any difference in environment of these sources? And the answer is yes, although we didn't provide any information about the environment. The environment information is already somehow encoded in the information of the acid in the acidity information of the galaxies. So, for example, for these 3 red galaxy classes, we see that the size is behaving different when it's moving to denser environments. So these 2 galaxy classes follow the trend of increasing sizes when moving to the denser environment, but this one doesn't do that. And this is something that is strange, because according to our thinking how the massive elliptical red galaxies has formed is really simple. So at first, the red galaxies, red nuggets, were formed really compact red small galaxies. And then through merger activity, they grow in size and in mass, right? So this would explain also why the size is increasing when moving to the denser environment, because when we move to denser environment, to clusters, to groups, there is more galaxies, so there is more interaction, the merger processes is more frequent. But there is a class which doesn't follow this relation. So apparently there is a subclass of red galaxies that doesn't follow this scenario and avoided this step. And apparently these red nuggets that survived skipping this phase of merger processes is found in the local universe. But so far the studies are limited to the catalog of less than 100 of red nuggets at local universe. So we wanted to look closely in these galaxies in this class, and we found out that we have 77 red nuggets at intermediate redshift. So this is the first sample discovered at intermediate redshift and doubling the number of known red nuggets. So we were also interested how looks the environments of these red nuggets. So far, the limited studies of red nuggets in the local universe shows that they are dominating in the clusters and groups, which seems contradictory to our logistic thinking, because if in clusters and groups the merger processes are more frequent, we should rather red nugget expect in the less in low density environments, right? So we have looked how our sample of red nuggets behaves, and apparently it can survive in both, in low density and high density environments. And we suspect that in low density environments, they can survive because of the low densities and lack of the interaction. But at high densities in clusters, the high velocity of clusters is just preventing those galaxies from any merger processes. But we also have found that the relation for the red galaxies found by Dressler and confirmed by us at higher redshift, when the red galaxies are, the fraction of red galaxies is increasing when moving to the denser environments, is driven only by normal sized galaxies. Although the compact galaxies can survive in high density environment, they are not so frequent, and the relation is driven only by the normal sized galaxies. So I hope that I succeed in showing you that multidimensional automatic galaxy classification is able to reveal in a totally automatic way galaxy population, galaxy classes that are super hard to distinguish with more traditional standard classifications tools. So I was focusing only on this red nuggets, but we have also found really interesting classes in more green area and in the blue end. Especially interesting work was done on the broadline AGN, and but I will not spoil it. Just stay tuned, because really soon the press release about finding overmassive black holes in Vipers-Above galaxies should appear, which is the work that we did with Mar. So I hope that she will be able to present this work further, and I will leave you with the summary. Thank you.
Thank you very much. So, are there any questions?
Can you say how overmassive are these black holes?
Oh, you have to wait for the press release. Mars, do you think it should be the next week? Yeah. Yes, these are the outliers, but it's really interesting, and I really encourage you to trace the press release, because we are having the new scenario, which is in contradiction to the standardly accepted scenario of synchronized growth.
Can you put again, you had a plot where you showed 3 different classes with AGN, passive, and star-forming galaxies, where you showed different paths somehow of evolution from redshift 1.2. This one, yes. And you mentioned that in AGN, you don't see this effect.
Yes.
Can you show this from the plot? Because I'm not sure.
So, okay. So, looking at the passive galaxies, right? We are starting at high redshift, and we are ending up at low redshift. And we can see the branches, how they appeared, right? And in case of AGNs, we don't see. There were already 4 different branches which never had divided into different
Okay, so
these
the
are
number
here.
on top are just the
the classes. So these are the so the idea is that we at high redshift we have quite a homogeneous classes of passive and star-forming galaxies. So we found basically, roughly speaking, one class of passive galaxies and one class of star-forming galaxies, which evolved in case of passive galaxies into 4 classes at low redshift. So the diversity of the the passive population has increased into this pattern. But this is not the case of the AGN. They were diverse already at redshift 0.1.
Over how many sources you can actually follow agents from redshift 1.2 to redshift 0.5 and so.
So of course this is very limited because of the redshift and the numbers, because I think that the AGN sample is few hundreds, and we still don't know exactly. We didn't look at this. We're focusing on the passive branch, but this is something that is still going to be investigated.
Yeah, so thank you very much. This is very good for us also understanding the evolution of galaxies and in a very a good graphic way. About this slide though, I was wondering, does the algorithm kind of normalize for the number of objects that you have in each class? Because for different redshifts, you expect to have different contributions from galaxies of different types. So if this is not properly normalized, you will create or destroy classes while there is a procession, a progression of the classes.
Okay.
And also related to that, trying to see that from an evolutionary point of view, I don't understand how the physical interpretation can be held if you have also an agent class where in principle you could have a star forming or a passive galaxy being in a class for 1 gigayear, for example, and then it's turned off. It's not a different evolution of the whole galaxy and its stellar matter.
Yes, so this is the schematic way of showing our studies. Of course, when we say here the AGN, I don't mean that here we don't see also the AGN, is that these are only the AGN. And here we can at some branch see also the AGN. But I would suspect, so this is still ongoing, but this would rather correspond to the broadline AGN when maybe the fraction of AGN is higher, and that's why it forms totally different branch according to the normalization question. So honestly, the process how we achieve this tree is really complex, and so we were trying to account for differences in the clusters and not to destroy and not to also find a new class that doesn't make sense in the physical meaning of being separated. So we started with with the classification of galaxies in different redshift beams. So each redshift beam has covers the space of 160 megayears. So we have 26 redshift beams. Then we ran the algorithm. We found the classes, a few classes, let's say around 10. But then we found that at different also redshifts and different classes, the scatter is quite huge. So let me just show this. So you can see that the scatter of this class, for example, is much higher than this. So we added another thing to our approach here, namely the classes that are very scattered. We classified again. So within the classes, we defined another classes to differentiate it more. we try to account that all classes has to have different properties, but we end up with even 20, 30 classes in each redshift. And then we used another machine learning algorithm to find how these classes successively can be merged together in different, going from one redshift to another redshift. And you can, and the number of classes are covering, I don't know, some classes have 10 objects and some classes have few hundreds of classes. So we really paid attention to not lose and not to also add information that is not existing. I don't know if that, but if that it makes sense to you.
Well, I was going to ask very similar question, but phrased a little bit different. No, it is the branching is not due to just Malgorzata bias, basically that you are only sampling the most luminous objects at high redshift and much earlier.
So this, of course, can be somehow done. So we are using the rest frame spectra to do that, and we try to do the mass complete sample that we somehow reduce the bias, but still this is something that we are taking into account in the physical interpretation of the properties of each branches. But so far we see that there is something more that can be only explained by the magnesium bias.
The other thing, whenever you do the unsupervised learning, do you use redshift as a label or not?
Yes, but honestly, the results don't change much when we drop it, because we are using absolute magnitudes or the rest frame spectra. So we are trying to remove the redshift information, but of course it's not trivial. So we prefer to stick and add redshift as the feature, but we didn't find that it's necessary.
Well, you use absolute magnitude, you use it somehow.
Yeah, exactly. The information is already encoded.
More questions? Maybe from Zoom? I have a curiosity, maybe from nuclear point of view. These 12 classes that you found, and also, I mean, you recovered basically as far as I understood, both in the American classification. Are there different also from a morphological point of view? I mean, from the morphological point of view, you can find 12 classes very distinct, or many of them fall in the same morphological.
So making the morphological classification is quite hard here, because all galaxies looks like the points. So we looked at the static indices here and the sizes of the galaxies, and we see that they are changing, but we would not dare to do any more sophisticated analysis of the morphologies. However, with Elena Sanchez Dominguez, we compared the morphologies of our classification of Viper's sources with the morphologies that Helena has derived within the DES project. The sample is really limited. It's only a fraction of matches between DES and Vipers. So I wouldn't say that this is a representative sample, but we found the correlation that our broad correlation with our red galaxies truly correspond to the elliptical galaxies, and blue to the spiral ones, with green somewhere in between. But of the lack of the more matches, we couldn't do anything more.
Okay. Any more questions? I don't know, online. No, I don't think so. Okay. If not, we can thank Shira again.
Thank you. Thank you.